Hi, I'm Oliver, and welcome to the first episode in the GCSE Computer Science series. This episode will cover everything you need to know about algorithms, an important part of all computer science exams. I'll admit they're pretty boring, but it's something we all have to deal with. However, they will become useful in understanding the logic of a computer later. So what exactly is an algorithm? According to AQA, an algorithm is a sequence of steps that can be followed to complete a task. Algorithms don't have to be portrayed as scripts coded in high-level languages. They're more, let me take this input, deal with it, and then output something. They're meant to be written instructions that are at the base of any computer program, and this is what we call pseudocode, but we'll get more into that later. In other words, input, control, and output. Input, process, and output. Let's use an example. Mr. Kennedy has a database that contains records for every student in the school. Now let's say Cameron Goodchild has been a naughty boy and Mr. Kennedy needs to send an email home to his parents. Luckily, Mr. Kennedy has made a program to prevent him looking through the whole database to manually find his parents' email address. First, the input. Mr. Kennedy types in the student's name and what form group he was in. Secondly, the process. The program will take that information and search the database for any records that contain the input. Finally, the program will output all of the information linked to the student it found in the database, allowing Mr. Kennedy to view the email address he was looking for. This is a very simple example of an algorithm. From it, you should have been able to work out what input, process, and output mean. This is an essential principle you should understand, as every program takes input, processes data, and outputs information. A more common algorithm that might come up in your exam is something called bubble sort. It's used to order items in a list. In this case, we've got 5 numbers. Let's say we want to put them in a descending order: 3, 8, 2, 4, and 5. We'd start with a loop where we can check if the first number is more than the second number. So we know that 3 is not more than 8, therefore we're going to swap the numbers over. And look at what we've got now. And let's do it again with the second and third numbers. 3 is more than 2, so we'll leave it how it is. 2 is not more than 4, so we'll swap them over. Finally, 2 is not more than 5, so we'll swap those over. And now we've got 8, 3, 4, 5, and 2. Not quite in the right order yet. Because we swapped numbers around, we need to run it again. And because we swapped that time, let's run it again. Now we'd run the loop again because there was a swap, but there will be no swaps because we managed to put the numbers in the order highest to lowest. Yay! I hope that wasn't too complicated, but just remember that this whole swapping numbers thingy is called bubble swap. No idea why, there's probably some clever reason.
Oh!
Okay, apparently it's called bubble sort because the larger numbers bubble to the top of the list. I don't see what was wrong with aeroplane sort. Like, they fly up to the top? Oh, I don't know. Now let's compare another kind of algorithm. It's called binary search. Just a quick note, don't worry if you don't understand these example algorithms. They can take time to wrap your head around, but give them another try after watching this video and they'll start to make sense. First, let's make sure we know what an array is. We'll go over this in a bit more detail when we talk about data types, but for now, just remember that an array is a special variable that can hold a list of values. You'll definitely go over it at some point. So let's make an array. 5, 7, 10, 20, 23, 34, and 56. These are all the numbers we put in our array. Now let's assign positions to each value. Remember that in programming, we start at 0 and not 1. Okay, let's say the program needs to find the position of the value 23. Rather than checking every single position to see if it's there, we have a much faster, more efficient solution, and it's called binary search. First, we have to find the middle value. The computer works this out by taking the lowest position and adding it to the highest position minus the lowest position, and then you divide that by 2. So 0 plus 6 minus 0 divided by 2 is 3. Therefore, our middle position is 3, which is correct. So does the value of 3 being 20 equal what we're looking for? Nope. Is 20 less than 23? Yep. So we'll travel to the right because we know we need bigger numbers. Now let's try it again, except this time our lowest position is going to be the previous middle position add 1. So it'll be 4. Time to find the middle again. So 4 plus 6 minus 4 divided by 2 equals 5. Is 34 equal to 23? Nope. Is it less than 34? Yes. The middle position is going to be 4 plus 4 take away 4 divided by 2, which is 4. Finally, we'll check the position of 4. Is it equal to 23? Yes, it is, finally. Now if you thought that was a lot of work, could you imagine a computer trying to find this one number in a huge array and checking every single position one by one to see if it's there? That's a lot of work, and it's what we call linear search. Checking every single element in a list until you find what you're looking for. Computers rarely use this, but by adapting the binary search algorithm, the computer can locate the position much faster. Those are the basic algorithms, and they should cover what you'll get in the exam. But the specification mentions merge sort and insertion sort, so just to be safe, I'm going to cover them anyway. If you'd rather not listen to me explain these, just click the card in the corner of your screen now to skip past this bit. So, merge sort, this might take a while, but stay with me. We learned how bubble sort can arrange numbers in the order you want by moving along the sequence and swapping values over multiple times. With merge sort, we split a larger set of data into blocks. Let me show you. 78, 64, 32, 52, 44, 12, 38, and 22. There's 8 random numbers. Now let's split them into 2 chunks. The order doesn't matter yet. 78, 64, 32, and 52, and 44, 12, 38, and 22. Okay, cool, now let's split them again. 78 and 64, 32 and 52, 44 and 12, and 38 and 22. So now we've got 4 pairs of numbers. What are we going to do? We're going to order them. The computer checks if the first number in the pair is greater than or equal to the second number. If it is, it'll put that number last. If not, it'll put it first. Watch this. We have 78 and 64. 78 is more than 64, so we're going to write them down as 64 and 78. Now let's try another. 32 and 52. Oh, will you look at that. 52 is greater than 32, therefore we're going to put 32 and 52. Now do that for all of your pairs. Here, we're going to put them back into 2 chunks again. We'll start with the first pair's first number. Is 64 less than 32? Nope, put 32 first. Is 64 less than 52? Nope, put 52 next. Then we can add 64 and 78. Then just do that again with the other chunk, and you'll end up with this. 32, 52, 64, 78, and 12, 22, 38, and 44. Almost there, let's reassemble the numbers as one chunk. Start off by comparing the first number in each chunk. Is 32 less than 12? Nope, put 12 first. Alright then, is 32 less than 22? Nope, put 22 next. Is 32 less than 38? Yes, put 32 next. I think you're seeing where this is going. In the end, you would end up with this. 12, 22, 32, 38, 44, 52, 64, and 78. If you didn't understand that, click the card above and watch it again. It might seem confusing at first, but watch it again and eventually it'll click. The final algorithm in the specification is called insertion sort, and honestly, it's horrible. Compared to bubble sort and merge sort, it is very long and can take forever. To put it simply, insertion sort is where you check every element before in the list. Let me explain. Here's another set of numbers. 1, 3, 8, 7, 12, 13, 4, and 15. We start by leaving the first number alone because there is nothing behind it to compare with. The second number, 3, we can check. Is 3 less than 1? No? Leave it where it is and move on. The third number, 8, has 2 numbers to compare to. Is 8 less than 3? No? Then move on. But wait, is 7 less than 8? Yes! Let's move 7 in front of 8. Cool. Now let's see if 12 is less than 8. Nope. 13 isn't less than 12, but 4 is less than 13. So we move 4 in front of 13. Hang on though, we've got other numbers to check. Is 4 less than 12? Yes. Move it before 12. Is 4 less than 8? Yes. Move it before 8. Is 4 less than 7? Yes. Move it before 7. Is 4 less than 3? No. Move on. Finally, we can check if 15 is less than 13, but it isn't, so we stop. And now you should have a perfectly ordered list. 1, 3, 4, 7, 8, 12, 13, and 15. That's nice, but it took a while. If you had a longer list, say one with 200 numbers, you might end up checking 150 of those to see if they are less. That would take a while, right? Well, a few more milliseconds is a while when processors have to do hundreds of things at once. And you can see it's slightly similar to bubble sort, except with bubble sort, you'll only check again if you know there is a chance of the order being incorrect. Once again, this is a little tricky, so please stick with me, and if you don't understand, watch it again. Now it's time to talk about how you can interpret and present your own algorithms. This is far more important than knowing those common ones, and you'll almost certainly cover this in your lessons. The first way of presenting an algorithm is through something called pseudocode. Pseudocode isn't a strict format with rules you have to follow. There's no dedicated syntax because it's up to you to format it. In other words, you don't have to use brackets in your pseudocode if you don't want to. All that matters is that your code is correct and that it is understandable by programmers with common sense. You'll also need to make sure your code is capable of running on the system it's designed for. This doesn't mean program it in a language a compiler will understand, it just means that what you want to ask the computer to do is actually possible. Let's take a look at some pseudocode I wrote. It's a game where an imaginary die is rolled and the user has to guess the number. While that code may slightly resemble the syntax of a high-level programming language, it was completely made by my head thinking what's appropriate. In fact, I'm going to call this OliverCode. Just kidding, but take a look at the code. The point is that you can clearly understand how the code is flowing. Even a non-programmer with a little common sense can work this one out. First of all, I'm saying that my random number variable is going to be a random number between 1 and 6. Secondly, I'm asking the user for some input by saying, what number do you think was rolled? Then I check to see if the user's guess is the same as the number rolled. If it was, I output a congratulations message. If it wasn't, I output a message telling them so. As you can see, it's pretty straightforward. You're going to be writing your own in the exam, so if you want to go getting used to pseudocode, I'd suggest opening a text editor or just grabbing a pen and writing your own. Think of a scenario, or think of a program you'd like to create and make your own pseudocode for it. Finally, there are flowcharts. Flowcharts are a way of displaying how a program, well, flows. Flowcharts can be applied to things outside of programming too, such as real-life scenarios. But check out this example of a flowchart. It's again for my die guessing game. The arrows indicate the flow of the code and what should be executed next. The oval symbol represents a start or stop point. In this case, my program is going to loop forever, so all it needs is the start point. The start oval points down to a rectangle. Rectangles represent processes, a point where the computer should think about something. In this case, the process is to generate a random number. After that, it flows down to a parallelogram. This represents input or output to or from the user. I'm asking the user to input their guess. Next, you'll see a diamond. Diamonds are most commonly used for if statements, but they're used to make a decision. If this is, etc. So if the random number is equal to the guess, it'll flow through the yes arrow and output, well done, you won. However, if the decision is false, it'll flow through the no arrow, and better luck next time will be outputted. Finally, they both join back together again, as the program flows into a single arrow right back up to the start. It'll continue looping. It's important that you know the difference between these four basic symbols and arrows. To retaliate, the arrow shows the flow of the program and the relationships between states. The oval can be used to start or end the program. In some circumstances, there can be multiple endpoints. The parallelogram will allow the program to collect input or release output. The rectangle is used to process something, and the diamond is used to make a decision and compare values. As long as you know the symbols, understanding flowcharts should be pretty easy. You might want to have a go at making your own. Maybe draw a flowchart showing how you would go about making a sandwich. That's quite a common example. At your school, you might use software like Flow or Universal Logicator to make flowcharts. In fact, you might have done flowcharts in other subjects like DT, but in the exam, you'll be expected to understand example diagrams, and you'll be expected to know how to create your own. Phew, well that's algorithms. Pretty long video. Remember, if you struggled at any of the sample algorithms, please watch them over again. If you're still struggling, or if you have any questions, type it down in the comments, and I'll respond as soon as possible. You can also private message it to me, but remember that others benefit off your question. If you learned something, please give this video a thumbs up and subscribe for more computer science videos as well as interesting things, where you actually see my face looking at stuff. This concludes episode 1 and I'll see you guys next time.